The topic of this session is about scale up or the development of new technologies in the water industry, because that is not really straightforward. So if we look at some introduction, then yeah, we can highlight a little bit or explain a little bit how that works. When you develop a new technology in the water industry, yeah, what are the challenges? How long does it take? So yeah, let's first look a little bit at that. So this is what we are going to do next. So Simon, if you go to the next slide, please. So yeah, agenda for today, small introduction of this session, the objectives of this project. So really the focus of this webinar, which are the reactor scale up, the design of a new system. We are going to introduce the system very soon. And then how do you go from pilot to full-scale operation, not only successfully, but also within a reasonable budget and time? Because within as you are a technology company, this is very important, time to market and also the development efforts. We will conclude with some conclusions, insights, discussion, and also finally also Q&A. But Q&A is important. If you have any questions, please drop them in the comments. We will be continuously monitoring the comments field and bring your questions live and answer them live. So let's have a lively discussion. We invite everybody to really comment a lot and question a lot. Okay, so let's start with innovating in the water industry. So first of all, innovating in regardless of what industry you are in is not easy. Yeah, also in the water industry. So for example, the topic of today is MBR's, membrane bioreactor technology. Yeah, when you look at this PhD thesis of Paul O'Callaghan, which is called Innovations in the Water Industry, a very interesting PhD thesis to read. I would highly recommend it. It's the thesis I have sent to most of people all over the world. Well, it says that it can take quite a while. Here we see the example of MBR technology on the slide from left to right. Yeah, when it starts from development, early piloting to commercial stage. And what you can see already is that it can take quite a while. So in this case, mainstream or really market breakthrough of or commercialization started around 25 years ago for MBRs. And when you zoom out to any other technology, what's written here on this slide is 300 technologies, yeah, have been investigated between a certain period from 60 research institutes. Only 10% of them, less than 10%, successfully were licensed, successfully reached the market. So yeah, there is a challenge, there is a barrier, and it's capital intensive, and it takes time to develop new technologies. This is a more general view. Also, MBRs are included here. But what this figure shows is the impact in the market after a while. So you have three stages, yeah? The dark blue, the light blue, and the gray stage. Gray is really above half a billion revenue or sales in that technology, yeah? So all of these technologies which have gray areas at the left, they are really core technologies in the market. For example, MBR is now for 10, 15 years a core technology with over $500 million global revenue, yeah, or sales. Other ones are UV or UASBs, anaerobic technologies. And you can see that others are following that cycle. And at the right, you can see a detailed table of MBRs and the number of sales. And you can see from 2008, the half billion was reached, and now we are above 1 billion in annual revenues, global revenues in MBRs, 1.250 million to be exact. Okay, so yeah, thesis to read. A lot of challenges related to development and scale up are also the piloting, because when you start piloting or developing a technology, it is hardware intensive, and before you start something, especially in a biological treatment system, it can take quite a while to see the impact. So it's often a trial and error-based process that can take quite a while and can consume a big part of the development cycle. So our company is trying to accelerate that. That's what you can see at the left. So we work throughout the whole technology lifecycle as AM team. So we start from early R&D with technology companies to final operation with end users. That's at the right, and everything in between. What is in between is the selection and the design of technologies before they are built. Yeah. So we built computer models to accelerate and optimize a lot of these processes at a global scale for technology companies, for end users, and also we work a lot with engineering firms. When we specifically apply this to MBR technology, and that's what's on the next slide, we see what we have tried to do here, how we have tried to support Maezawa Industries. So you start with a rather small pilot plant, and a pilot plant that shows the power of that new technology, which is the BMBR. But Naoya will explain more about that specific technology later in this webinar. Then we help with a virtual scale up. So we help designing virtual full scale or larger scale plants, let's say, larger demonstration scale plants using computational fluid dynamics with some kinetics. And that's what Simon is going to talk about. Then you can really build such a plant. And one of these demonstration facilities is what you see on the picture currently operating in Tokyo in Japan. So this is quite a nice story because we started from a pilot, or at least Maezawa Industries started from a pilot that was initially developed at a university in Sapporo. And then finally, now currently a very big plant is already operating. So that's a nice closure of such a story. So I think we should give the floor to Naoya.
Thank you for the kind introduction, Wim. Hello, everyone. Thank you for being here today. My name is Naoya Tamura from Maezawa Industries. In my 10 years of experience in the water industry, I was responsible for the success of water filter system for Japan and US markets in my previous company. And also in Maezawa, I was part of a team that successfully implemented the BMBR technology, which is subsidized by Japanese government. I'm glad to introduce our collaboration today. Before we start our presentation, let me just remind you, if you have any questions, don't worry, we prepared Q&A session at the end of my presentation. First, let me introduce our company profile. Maezawa Industries have been providing solutions in the field of water and environment in Japan. Maezawa started our business by manufacturing high-quality valves and gates for waterworks and supplying for over 80 years. And Maezawa have expanded its business to water treatment by providing various water treatment systems and creates unique technologies. Please move on to next slide. Okay, BMBR is one of our current challenge for creating further energy-saving technology. Membrane bioreactors has many advantages, including excellent treated water quality and small footprint. However, high operational energy consumption of MBRs disrupts its widely application. The usual configuration of the MLE-MBR has two tanks for aerobic and anoxic reaction. In BMBR, the single tank, which is separated into two zones by separated by inserted baffle, promotes nitrification and denitrification. At this time, I'm going to play a short video clip that explains how
So we have a little technical issue at the Japanese side, but we try to bring our guest Naoya back. In meantime, I can shortly introduce this BMBR concept. So BMBR stands for Baffled Membrane Bioreactor. So it's an MBR technology, and we have seen in the previous slides that this technology exists quite a while already, and it's commercial for more than 20 years now. But BMBR makes it more specific. So Maezawa Industries tries to unite all of the different compartments of an MBR system in just one reactor by installing a baffled. So that gives the name baffled MBR. So this baffle you can see on the figure, these are these black vertical lines in the middle, surrounding the membrane, surrounding the aerators, okay? So this MBR system works in an sequential mode as an SBR. So the water is going up, and that's what you can see at the left side. When the water is high, the oxygen reaches the whole tank, it circulates around. But when then the water or there is no feed anymore, but you keep pumping permeate, then the water reaches a certain level, below the baffle, and then the oxygen cannot enter the outer shell anymore and turns anaerobic or anoxic. Yeah, and then you get denitrification. So this is a concept with the aim of limiting the footprint, like Naoya was explaining, but also limiting the pumping costs, for example. Yeah. So that's really the concept of this BMBR technology. So if we go to the next slide here, maybe I'll give the floor to Simon to explain a little bit the project.
Thank you, Wim. So yeah, the project objective is mainly to go from the pilot scale to look, okay, what is now the pilot scale? Is it how does the design looks like? Is it well designed, or are there certain things that we can improve? And after this part, how do we move to the next step to scale this pilots to a large pilot plant, and afterwards even to a full scale? So Naoya is back. So back to him.
Sorry for the inconvenience. So let me introduce this slide. AM team and Maezawa collaborated to find insights of BMBR with a size of 4 cubic meter tank called a small pilot plant. In MBR, cost bubble aeration is essential for mitigating membrane fouling. Our previous study shows that operational energy consumption of BMBR will be considerably decreased if 3-meter high membrane element with the same cost bubble aeration could be operated. Therefore, we suggested a large BMBR pilot plant with a water depth of 4.8 meter. However, Maezawa didn't have criteria for scale-up. Where is a suitable position of baffles, disk aerators, and membrane unit? Therefore, we tried to find a proper scale-up by using CFD. In order to explain in more detail, let me welcome Mr. Simon Ducci. He's a project manager at AM team. So please welcome Simon.
Okay, so I will give a little bit of more background on which models we use at the AM team. So we mainly use two types of different models. So one is a computational fluid dynamics called CFD. Is a well-known tool, I think, in hydrodynamics, where you can just simulate the hydrodynamic behavior. So you just put in the real 3D geometry inside your program, and you just can check how the water is flowing or the fluid is flowing in general, gas flows. 1, 2, 3 phase, depending on which situation you are. The other type of modeling that we are taking into account, or that we do, is the kinetic modeling. So that's more a CSTR, so you can see on the figure at the right bottom the typical trains. So what you do there is more this model type makes you able to do dynamic simulations, where you really put in the whole time series, where you can check also what is the impact on the daily pattern, for example. So it's very dynamic, while in CFD it's more useful to use steady state simulation, so steady conditions, to really look at the design optimizations. So that's, for example, also what you can see at the bottom left, where you can really see 4 different designs, and you can just compare, okay, what is now a good situation? What do we want to achieve with the design? Is the flow pattern as we want that it is? Can we just, for example, add an extra mixer if you want more mixing? Do we want to an extra baffle if you want an extra baffle? All these things can be easily tested virtually, and that's how you can create the design. Once you have the perfect design, or you have an optimized design, we can translate this model, this CFD, into the kinetic model. So, and that's what makes us unique. We couple the dynamic modeling or the CFD with the kinetic modeling, and that's also what we have done for Maezawa in this project. And in the next slides, we will show you a few examples. So I can show you one example, which is this one. So, and now I will give a bit more other examples. So in this example, for example, what you can see here, so this is a CFD simulation where we really modeled the oxygen transfer from the liquid to the gas, where you can see, so the system. At the bottom, you see the diffusers. So you see the fine bubble diffusers. Then you see also the membrane unit at the right side, the rectangular block that represents the membrane unit. And underneath, you have the coarse bubble diffusers. So you can clearly see that at the left part, that's the anoxic zone. Normally, the flow should go from the left zone to the bottom, underflow to the aerobic zone, where then it goes up with the bubbles. You have an aerobic zone, and at the top, it flows over. What you can now see is that part of the air bubbles at the bottom flows to the anoxic zone. And that's clearly what you don't want, of course, because you are adding bubbles, air in your anoxic zone. So this is a great example to how we try to help Maezawa to optimize the design. And Naoya will tell us a bit more on this later. Another example that we could see here is that the fine bubble diffusers, the bubbles were going to the membrane unit, which means that these bubbles will not go into the main aerobic zone, but really going to the membrane unit, which is not really wanted. And also there, by changing a bit with the diffuser location, you can try to optimize this. So that's two examples, easy examples in one cross-section, because it's a whole 3D system, so much more conclusions would be drawn from this, but that's two easy examples to show what CFD and the kinetics are possible to do. So then I think it's time to go back to Naoya and to go more into detail. So what we really did in this project or one very great example of what we try to, or how we optimized the design of Maezawa.
Thank you for the detailed explanation, Simon. Let me continue with the result of improvement. The left scenario shows the prototype of the large BMBR pilot plant. Baffle locates at the center of the tank. The small opening at the bottom of the baffles introduce water from exterior to interior zone. Disc-shaped aerators discharge fine bubbles and promote nitrification. Membrane unit is set at the corner. However, some unexpected phenomena were found in scenario 1, shown in following slides. Then we also conduct simulation in scenario 2. Hunches surrounds membrane unit for changing the water flow. So let's proceed to the next slide. So as we can see, these charts show the simulation results of flow velocity vector at the horizontal plane under the disk aerators. Bright colored arrows show high velocity, and dark colored arrows show low velocity. In scenario 1, water goes straight forward from opening to membrane unit. So it is indicated that we still have issue of oxygen transfer because of this short circuit flow. Then we added hunches in scenario 2. The aim of this hunches is physical barrier between membrane unit and other areas. As a result, the short circuit flow was not found in this scenario 2. As we can see, these charts show the simulation results of gas hold-up distribution at the vertical plane. The plume from disk aerator to the membrane unit was found in scenario 1. This is due to the drawing flow we could see in previous slide. Fine bubbles get together with coarse bubbles, and oxygen transfer will be decreased. On the other hand, there was no specific drawing flow from the opening and disk aerators to membrane unit in scenario 2. So hunches improve the flow pattern and mixing condition dramatically. Okay, in conclusion, we conducted a scale-up by getting insights from the CFD simulations. A small BMBR pilot plant was used to find fundamental technology of BMBR and rapid prototyping. For scale-up, we need additional criteria. Then we conducted virtual prototyping. CFD funds the interaction of flows and influence on the oxygen transfer. Based on these insights, we attempted to improve the configuration. Finally, the simple way of adding hunches changed the circumstance dramatically. Then we could move on to construct large BMBR pilot plant with confidence. But we know, of course, CFD simulation was simplified model, but we know important points for designing, and also we know the key points for sensors in the tank. We have currently performed continuous operation of a large BMBR pilot plant and accumulate data. It needs to run validation in the municipal wastewater plant to see impacts on seasonal change of the influence. That's all my presentation. So thank you very much for your kind attention.
Right. Yeah, thanks so much, Naoya and Simon, for sharing your thoughts on this BMBR project. I think we can have a webinar on this for maybe 3 hours or 4 hours or 5 days, because this is a project or a collaboration we have for many years already now. I think we have built a very good relationship, and some nice outcomes along the way came out. And yeah, now we had to summarize everything in one presentation, so it's hard. But yeah, first, before we go into the Q&A and the questions, I want to thank again Maezawa Industries and Naoya and your colleagues for this very good collaboration. So we still enjoy it as AM team, and we look forward to continuing it.